The Honorable Dean of Faculty of Agricultural Technology Brawijaya University, Professor Dr. Insinyur Imam Santoso MP, the Honorable Associate Professor Guido Grause from Tohoku University is our main speaker today, and beloved participants of today's event, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon.
Waalaikumsalam.
First of all, let us pray and praise to Allah Subhanahu wa Ta'ala. Because of His bless and mercy, we can come together without any obstacle here with healthy condition in the International Guest Lecture of Renewable Polymers. Second, let us greet and pray to our beloved Prophet Muhammad Sallallahu Alaihi Wasallam, who had brought us to the path of light and left the darkness in this life. Dear participants, before we come to the main session, let us start this by praying first so that the event that will be held today will run well without any obstacle at all. Pray based on individual belief begins. Done. Before I start, let me introduce you myself. My name is Fabella Aura Hendian Putri, and today, inshallah, I will accompany you as today's Master of Ceremony. And before we start, let me deliver the structure of the event today as follows. First, opening, and then we will have the greetings and opening ceremony by Dean of Faculty of Agricultural Technology, Brawijaya University, Professor Dr. Insinyur Imam Santoso MP. And then we will have the online photo session. Next, the main event, we will have the guest lecture of renewable polymers that will be delivered by Associate Professor Grause Guido. And then we will have the discussion. And last but not least, we will have the closing ceremony. Now we will invite the Dean of Faculty of Agricultural Technology Brawijaya University, Professor Dr. Insinyur Imam Santoso MP, to deliver his speech. To Mr. Imam Santoso, time and place are yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Wow.
Good afternoon, ladies and gentlemen. The Honorable Associate Professor Grause Guido from Tohoku University, the Honorable Head of Agricultural Engineering Department, Head of Environmental Engineering Department, Faculty of Agricultural Technology, Brawijaya University. And today, first of all, as a Dean of Faculty of Agricultural Technology, Brawijaya University, I would like to welcome all of you to our international guest lecture that will be present about renewable polymer. Thank you for being here with us today. I also express my respect and appreciation to organize this event, Head of Environmental Engineering Department, Head of Agricultural Engineering Department, and every team that already prepare and create this event. In today's gathering, our agenda is to learn about renewable polymer from Associate Professor Grause Guido from Tohoku University, Japan. Thank you and welcome to our beloved faculty and our international guest lecture. We know that the field of polymer derived from non-petrochemical feedstock is gaining a great deal of momentum from both a commercial and academic sense. Using annually renewable feedstock, such as biomass, for the production of new plastic can have both economic and environmental benefit. Many research, especially fundamental research in the production, modification, property enhancement, and application of this material is an important undertaking. So the new material concept and utilization of these that result from this effort will shape the future of polymer from renewable resources. We are very thank you for the Associate Professor Grause Guido from Tohoku University that already allocated time and will to share knowledge and experiences in research and many things related with renewable polymer. So thank you very much for everyone who joined with this event. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. That was the speech delivered by Mr. Imam Santoso. Thank you so much for your speech, sir. Moving on, now we will have the online photo session for everyone who can turn the camera. Please turn on your camera because we will have the online photo session that will be taken by the host of this meeting. Maybe everyone can strike a pose. Don't be too hard. Okay, 1, 2, 3. Next page, maybe. Okay. Next page. Okay, maybe that's all. Thank you, everyone. Okay, so now we have come to the main event, that is guest lecture with the theme Renewable Polymers, which will be delivered by Associate Professor Grause Guido and moderated by Mr. Fajri Anugroho. To Mr. Fajri Anugroho, please, time and place are yours. Mr. Fajri, maybe you can unmute the microphone first.
I'm sorry. Okay. Thank you very much for MC for giving me this chance for me to deliver this international guest lecture. Thank you very much for Dean of Agriculture Faculty, Professor Imam Santoso. And thank you for our speaker today, Associate Professor Dr. Klaus Guido from Tohoku University, from his presentation of the renewable energy. And I think this is very important for us because renewable polymer is now is very important to our country because now we have a lot of problem with polymer. So from this lecture, we hope that Associate Professor Dr. Klaus Guido can give us knowledge and experience about this renewable polymer. Now, I will give Associate Professor Dr. Klaus Guido to deliver this presentation about the renewable polymer. For Professor Guido, time is yours.
Thank you very much. Thank you very much for having me here. I just will see that I can share the screen with you. I hope you can see my screen.
Yes.
Okay. Thank you very much for having me here, for the nice introduction. My name is Guido Krause, and I'm from Tohoku University. Actually, I will not talk that much about my own research because my field is a little bit different, but I noticed that you are at the agriculture engineering department, and so I was thinking what could fit, because I'm actually a polymer chemist, and probably what I did most in the past was thermal degradation of polymers, which you are probably not so much interested in. So I was thinking to give you some knowledge about renewable polymers, what is now going on in research, what kind of biomass can be used, or what kind of materials can be used to produce polymers that are not derived from fossil fuels. How much time do I have before I start? Can you tell me about when I should finish?
I think 45 minutes. Yeah, 45 minutes, I think. Yeah, because we have 2 hours. Yes.
So about what is it? 1 o'clock at your time.
Yes.
Okay.
Yes, 1 o'clock. Yes.
Okay, so I will. So actually, this lecture is commonly a little bit longer, but I will keep the time. So we have in the past there were quite a lot of different materials developed, which have as the main source biomass, and the main reason for this was in the beginning not so much that fossil fuels are considered not a clean source, but more that that when plastic gets into the environment, it can cause harm, and so plastics that get into the environment would be better if they would degrade in the environment. And it is expected that biopolymers are biodegradable. This is not really true, but this was in the beginning the main reason. However, even though biopolymers or polymers derived from biomass do not make use that much of fossil fuels. However, they cause some other problems because they have a high consumption of energy and water for their production. You need agricultural means, which means fertilizer, pesticides, land use, and so on. And you have the problem that these materials, that the feedstocks for the production of biomass-derived polymers are in competition with food crops. So many polymers you can produce actually from eatable sources, for example, from starch, from sugar, and other polymers require at least land, which might not be available then for food production anymore. One misunderstanding I should explain at first. So materials or plastics which are derived from biomass are not necessarily biodegradable. A lot of polymers are, even though they are produced from biomass, have a very low biodegradability. And the reason is mainly that all plastics are in general have a low biodegradability because of the high molecular weight. And on the other hand, there are also plastics which are produced from fossil fuels, and also they are produced from fossil fuels. They might be biodegradable. So there's then the situation that for both for the biomass derived plastics and for the biodegradable plastics, the term bioplastic is used, which is sometimes a little bit confusing. Plastics or renewable plastics cannot only produce from a biomass, but you can also produce them from carbon dioxide. Carbon dioxide can react with certain groups, for example, with epoxide groups, as you can see it here on this figure. There you have also the possibility to make use of biomass-derived compounds, for example, limonene oxide, which can be obtained from limonene. This is a compound which is, for example, present in wood resin. Or you can make use of other epoxide, of artificial epoxide, then the polymer is not completely made from renewable resources. The advantage of carbon dioxide is that you can obtain it, for example, at least still, for example, from the recovery from power plants, or you can also get it from the atmosphere. Then okay, next I want to get to other polymers. So you can also produce conventional polymers from biomass. So, for example, polyethylene or polyethylene terephthalate can be obtained from biomass as well as from fossil fuel. I will talk about the way how to do this a little bit later. The sources for such polymers, or for a lot of other polymers as well, can be sugar from sugar cane, sugar beet, for example. These have actually the best opportunities because it is possible, because this kind of biomass is very easy to process. Other sources, for example, like wood and grass, can also be used. They are considered as second-generation feedstocks, while sugar-derived materials are called first-generation resources, because wood and grass are not in competition with food production. And so also the use of wood and grass can be used. Also starch from wheat and potatoes and maize is possible. However, these type of resources provide commonly quite low yields, so that this kind of starch producers should be avoided. The monomers that you can get from such biomasses are, for example, ethylene glycol, and also, for example, terephthalic acid can be obtained. Actually, these are monomers that are used for conventional polymers. So the advantage of these is that because they are the conventional polymers, and you obtain the monomers that you use for the production of the polymers are the same as you get them from the fossil fuel. You do not have to change the polymerization process itself. So you can use the common plastic processing technology as it is. Commonly, it would be better to use monomers which can be obtained in a better way from biomass. But for this kind of polymers, you need commonly to change the process technology. And therefore, because these monomers derived, if these monomers are derived from biomass, in this case, it is often not the optimal solution for the production of chemicals. One example of a polymer, of a conventional polymer that is produced from biomass is polyethylene. And polyethylene can be obtained from sugarcane. As you can see here, from the sugarcane, the sugar is extracted, then fermentation occurs. You get ethanol from this process, and the ethanol is then dehydrated, and you get ethylene. This is then called green polyethylene. However, still, this process is done in Brazil, and about 200,000 tons a year is produced. However, still, most of the ethanol in the world is produced from fossil fuel by the oxidation of ethylene. So in this case, it makes in the moment not so much sense to produce ethylene from ethanol. Another example for the production of conventional plastics from biomass is the production of polyethylene terephthalate. As we have seen, we can obtain from sugar or also from wood, we can produce ethanol. Ethanol can be dehydrated, forming ethylene. And ethylene can be oxidized to ethylene glycol, to ethylene oxide. And after hydration, we get ethylene glycol, which is one part necessary for the polyethylene terephthalate production. The other one is terephthalic acid. Terephthalic acid can be obtained in different ways. Here it's a little bit small, and I do not want to go into the details. However, you can see at the top the table, and there you can see the environmental impact of all these methods. And the important point of this is that the most viable process for the environment is that in which waste materials are used, not a biomass that is grown for the purpose of chemical production, but when the chemicals are produced from waste material, as in the scenario C, where limonene is obtained from orange peels, and then the limonene is then oxidized to terephthalic acid. Anyway, limonene and also other terpenes are quite common, can be obtained from quite a lot of different sources. And because of their double bonds, they are able to undergo polymerization reactions. The most simple terpene is isoprene, which is the monomer of natural rubber. So you know that natural rubber is a polymer that is used in a lot of applications, for example, for tires and also for other applications that require rubber. But more complicated or more other terpenes also can be obtained in wood resins, in citrus fruit peels, and so on. And these can be polymerized. One, you can see here polybetapenene as one example. The properties are comparable, for example, to polymethyl methacrylate, which is used as, or which is known as organic glass. It has a high optical transmittance and, however, a quite low molecular weight. This is an obstacle of this quite not so easy to polymerize material. Other monomers or other materials that can be used for monomer production is, for example, vegetable oil. Also, there's the production of vegetable oil is in the range of 150 million tons per year. For comparison, the production of plastic in the world is in the moment in the range of about 350 million tons. So plastic production is about double as high as that of vegetable oil. And there you can see actually one of the obstacles that you have with biopolymers, that for being competitive with conventional plastics, you need huge production numbers. And for this, you need a lot of material and a lot of biomass, a lot of agricultural ground. And this makes it quite difficult for biopolymers to get into the market. Here you can see some examples for what can be done from vegetable oils. And you can see, and I want especially go to one example, that is the production of nylon 11 from oil. Therefore, you need first, when you have vegetable oil, then you need at first transesterification. You have to remove the glycerol, which can also be used for the production of polymers. Then you obtain ricinoleic acid, which can be split into two parts. At about 500 degrees C, you get 10 anticenoic acid, methyl ester, and heptanal as a byproduct. Then the methyl ester is hydrolyzed, you get the acid. The acid has the double bond which reacts with HBr, and after substitution of the bromine, you get an amine, which you can use then for the production of nylon 11. So you get a polyamide. This is now nylon 11, which is a polyamide. And whenever you find somewhere nylon 11, you can be sure this is complete polymer derived from biomass. So all the nylon 11 that is produced is from this route. Unfortunately, nylon 11, even though it is obtained from biomass, is not biodegradable, as commonly all polyamides are not. Also, sugar can be used as a feedstock for bioplastics. So we have already seen that we can produce ethene from sugar. We can also produce ethylene glycol, which we can use for polyethylene terephthalate. But there are much more possibilities to make use of sugar for the production of bio-based polymers. Mainly, we can use processes of fermentation. We can produce, for example, lactic acid. We can also produce polymers directly, like polyhydroxyalkanoates. It is also possible to modify natural polymers like cellulose, which is the base of celluloid and cellulose acetate, for example. And the disadvantage is that when a new bio-based polymers are developed, that these require new technologies. And often we find also that especially the fermentation process is quite water intensive, and the polymers from such processes are quite expensive. Here you can see some examples for sugar-based polymers like polylactic acid or polyhydroxyalkanoates. Now I want to introduce some examples for sugar or sugar-based polymers. One is, for example, thermoplastic starch. Starch can be obtained from a lot of different feedstocks, from corn, rice, potatoes, and the processing of thermoplastic starch is a quite simple one. You use only starch, you add water or ethylene glycol as plasticizers, and then it's extruded into a form, and you get thermoplastic starch. The disadvantage of this polymer, of this type of plastic, is that thermoplastic starch is probably the most simple plastic that is today used. It has very simple properties, and it can only be used for certain low quality applications. The main disadvantage of thermoplastic starch is that it is very sensitive to changes in the moisture, which means when it becomes in a dry climate, it dries out. In a wet climate, it takes up additional water. Another much more advanced polymer is polylactic acid. Polylactic acid is a material which is very competitive with common polymers, and it has quite a long history already. For example, it is used for packaging, for injection molding applications, which includes almost everything that you can make for household goods and so on. Also, it is used for agricultural purposes, for example, biodegradable mulching film, because PLA is really biodegradable. Therefore, it is also used for medical applications, for example, for threads. When you have a surgery and the wound has to be closed, the threads are used, and the advantage is they are degraded and they have not to be removed afterwards. The disadvantage of polylactic acid is that the glass transition temperature is quite low. Glass transition temperature for polymers is the point where crystallization occurs. So above the glass transition temperature, polymer that is able to crystallize can crystallize, and this commonly is when this occurs, then also the shape of the material changes. Another one is regarding medical applications. As I said, the threads are biodegradable and they have not to be removed. However, during the degradation of polylactic acid, lactic acid appears, and therefore, when the polymer degrades, the pH is decreasing, which sometimes can cause problems. Polylactic acid can be synthesized from lactic acid, which is obtained from the fermentation of sugar by lactobacillus. And then the lactic acid is obtained, then a condensation reaction is conducted, in which you get D-lactide. And after that, this lactide is polymerized by ring opening polymerization, and you get polylactic acid. Another polymer that can be obtained from biomass is polyhydroxyalkanoates. These polymer and these types of polymers are produced directly by bacteria. By quite large number of bacteria can provide this type of polymers. They use this as an energy storage. For example, as plants commonly store energy in the form of starch, these bacteria do this as polyhydroxyalkanoates. There are a lot of monomers known. About 150 different monomers can be produced, and also it is possible to get copolymers by changing the the process parameters, and also, for example, changing the feedstock. The feedstocks that can be used are, for example, starch, sugar, oil, plant oils. Also, waste materials can be used, sugar cane bagasse or rice bran. The properties of these materials are similar to polyolefins. They have quite a low melting point, which might reduce their applicability, and their price is quite high. But they are commonly completely biodegradable because the bacteria can use them as an energy source. The processing is a common fermentation process. So you obtain the bacteria which are able to produce PHA. Then the feedstock is fermented. The cells are precipitated. The cells are separated from the plastic, and in the end, the plastic is then dried and pelletized and can be used. Unfortunately, the most abundant biomass on Earth, lignin, is commonly not really used for polymer production. The reason is that the lignin structure is difficult to break, and the compounds that are obtained from that are difficult to use. However, some researchers actually found a way to obtain were able to produce decarboxylic acid from lignocellulosic biomass by funneling, which means that they stopped bacteria to produce other materials, and therefore their metabolic path always ended at this certain compound, which is 2-pyrone-4,6 decarboxylic acid. It is not known yet if this compound actually provides good polymer. If this compound is used, the polymer is certainly biodegradable because it contains a lot of attachment points where actually biodegradation can occur. So this might be a way to replace, for example, terephthalic acid by this kind of compound. So these were now mainly processes which can be used, which are based on biochemistry. However, there are also possibilities to make use of traditional methods of traditional chemical processes, for example, gasification. Gasification is a process where, for example, biomass is heated up at high temperatures in the presence of water or steam or oxygen. And by this, we obtain a synthesis gas, which contains mainly of carbon monoxide and hydrogen. And this synthesis gas can actually, again, be used for the production of hydrocarbons. There are today a lot of different processes available. As you can see, they have all different names, but the principle of these processes are all quite the same. They all are based on the Fischer-Tropsch synthesis. They just have some changes, maybe in the catalyst or in the temperature. But in the end, you can obtain hydrocarbons from them. And with these hydrocarbons, you can again produce polymers. For example, polyolefins. The nice thing of the process of gasification is that the gasification makes use of any type of carbon source. So it is not dependent on if this carbon source is, for example, sugar, starch, or lignocellulosic material. In this process can make use of everything. It can also make use of, for example, waste plastic or coal or oil. When we think on the production of biomass-derived plastics, we have also to think about the environmental impacts of such processes. So, a very strong impact has the land use. So you can see here how much, what is the required area that you need for the production of polymers, for example, for thermoplastic starch, per 100 kilotons a year, 130 square kilometers for polyethylene, for example, from sugar cane, 350 square kilometers, and for PLA, 900 square kilometers. You might think this is quite a lot, but you have to imagine that 100 kilotons a year production, this is a typical size of a polymerization plant. You had earlier the example of the Braskem polymerization process of polyethylene. They produce every year 200,000 tons. And in order to be able to compete with conventional plastics, it is necessary to reach also this size, which requires a lot of agricultural area. Then we, as I mentioned earlier already, this materials that are derived from biomass is in competition with food production, but not only with food production, but also with energy production, because it is expected that also energy production shall be in future more and more depend on biomass. So we have then already three main processes which require biomaterials, and this from this we will see that we will need more agricultural land as probably can be provided by the surface of this planet. And when we have you make use of agriculture, it is not just that we need more land, it is also that we have then to expect more impact of these agricultural processes, for example, eutrophication, ozone depleting chemical production. And we must also see that we will have more consumption of fertilizers and pesticides. So we have to see that also biopolymers, biomass-derived polymers, have an environmental impact, not just on the side of eutrophication and the use of pesticides and fertilizers, but also for the production of these materials, agricultural machinery is required. And machinery still needs fossil fuels, which means that even though these biopolymers are produced from biomass, they still contain a lot of fossil fuel. Here on the right side, you can see the amount of fossil or the global warming potential for plastics from cradle to gate, which means until it leaves the production facility. You see in this case that PLA and TPS are not so much different from conventional polymers. However, we have also to see that this is only from cradle to gate. It's not from cradle to grave, which means that when we have the conventional plastics here, and they of course contain also the carbon as a carbon source fossil fuel, which is not considered here yet. So when we think on cradle to grave, so until incineration, then we have to add another 4 kilograms per kilogram plastic for the conventional plastics, which means that some advantage is obtained from bioplastic when the plastic after use is burned. So if it is recycled, then this advantage is not that high. So we have to think, especially because of this kind of analysis, we have to think how should we actually make use of plastic and also on bio-derived plastic after use. So many people think because it's bio-derived plastic, it is safe to let it degrade in the nature, for example, by composting, by landfilling, or other methods. However, we have to think that also the production of biomass requires energy. And when these type of plastics are degraded in the environment after use, then all the efforts made for the production of these materials are gone. So we have to think that bio-derived polymers should be used also after it becomes waste. For example, by incineration, we can obtain energy from that, or better, when we can actually make also recycling of this type of polymers. This will also save resources, especially agriculture area. So, what opportunities do we have when we have bio-based polymers which became waste? So when these materials end up in landfill, we will probably obtain methane, which might be released into the atmosphere and increase global warming. Then we have the possibility to do composting. This would be carbon dioxide neutral, because the carbon dioxide in this polymers was obtained from the atmosphere, so it goes only back into the atmosphere. In the case of incineration, we can actually recover energy, and by this, actually, we can reduce the requirement of burning other sources of fossil fuels. So in this case, we can actually have a reducing effect on the climate change. And the last possibility is that we can also do recycling, which is for a lot of these bio-based polymers are difficult. Some can be recycled, others can be, for others it is difficult to recycling. So so in this case, we have the possibility, for example, to make mechanical recycling, which can reduce water consumption and agricultural impact. However, mechanical recycling produces commonly quite low quality materials. We have other possibilities, for example, chemical recycling, which is possible for some polymers, as we can see here. For example, for polylactic acid. Polylactic acid can be mechanical recycled. It can be also chemical recycled. Chemical recycling is, for example, hydrolysis. In that case, the lactic acid is recovered, and it can be used again for the production of PLA. Also, thermal degradation is possible. So the polymer is heated up to temperatures of about 500 degrees C, and then we obtain lactide as a product. Also, lactide can be used for the production of PLA. Polyhydroxyalkanoates are much more difficult to recycle. There is the possibility is, for example, to do mechanical recycling and blending with virgin material, which provides then a material that has lower lower properties than the original material. However, we can reduce the environmental impact by this to some extent. A chemical recycling is difficult. Polyhydroxyalkanoates are destroyed, so the monomers are destroyed, and therefore it is not really applicable. What is possible is to feed polyhydroxyalkanoates to bacteria. And these bacteria are able to produce from the used polyhydroxyalkanoates new polyhydroxyalkanoates. Thermoplastic starch cannot be recycled at all. Of course, these materials can also be degraded in the nature, so by biodegradation. So if biodegradation is possible, these materials are removed from this and these materials are decomposed and mineralized, and there's no opportunity, you do not get anything valuable from that. The biodegradation itself depends on the composting and on the soil properties and on the water availability, and it commonly takes from months to years, also for biodegradable polymers. Composting is the fastest process. There, it commonly takes only the complete degradation of polylactic acid or PHAs. Then takes only a few months. In nature, where the conditions are not that optimal, it might take several years. This is my outlook. So we need to think more about bio-derived polymers. We need actually polymers which can be produced in large amounts, and this at a lower cost and also at a lower environmental impact. The point is that one point of bio-derived polymers is also that when we come to a decarbonized world, so when fossil fuels are not used for combustion processes anymore, there will be no fossil fuel production just for the chemical industry. Therefore, then in that case, biomass has to replace fossil fuel in this field. And this we have to consider, that we need to think about that actually the carbon that is used in the industry needs to be recycled, and so that the environmental impact is kept as low as possible. Thank you very much.
Thank you very much. Your lecture is very interesting. I know that there are several kind of biopolymer. Yeah, it's can be easy to take, but a lot of biopolymer cannot create easy, and so we have to consider about a lot of things. Yeah, particularly chemical that can disturb the environment. So I will open for the question. If you have any question, please say your name and deliver your question. Okay. We wait for some questions. I will ask to you, Professor Guido. Can you explain about the biopolymer production in Japan recently? Yeah, in maybe 2 to 5 years is about biopolymer production in Japan.
Okay, you want to know how much biopolymers are produced in Japan, and
yes.
I think that in Japan, still most of the polymers are produced on the conventional way. So Japan does not have so much agricultural ground, so which is quite a limiting factor for this of processes. So I'm not familiar with processes that are now in Japan. There might be some, but I do not really know about them. You have to see that Japan has not so much, so much possibilities to achieve biomass, and therefore it's quite difficult in Japan to do such things.
Okay, thank you very much. Yeah, I have one question from students. Good afternoon. I'm currently taking bioprocess engineering as my major. This is Rahma Rizky. Yeah, I would like to ask the question about the biomass as a source of energy, such as in Brazil. Some also use it to produce bioplastic.
Yes.
The question is, why do you think other governments from other countries are reluctant to focus on the biomass derived polymers productions? Yeah.
Okay, this is an interesting question. So you want to know why why it is difficult to introduce bioplastics into the market. Well, the most important disadvantage of biomass-derived plastics is that they have quite high production costs. So they have the disadvantage that fossil fuel-derived plastics are actually are in the market, and it is quite, and they are well developed. They were developed over the last 100 years. So this is something where actually biomass-derived plastics have actually first to get through. They use very different methods of production, and therefore you need new production facilities. new processes, new new processes, and it is quite difficult for biomass-derived polymers to get into this, because the fossil fuel-derived plastics are already optimized for the applications they are used for. This is so they have mainly something like an something like an advantage of being introduced already 60 years, 70 years before the first biomass-derived plastics were developed, and therefore, as these polymers are quite late, it is difficult for them to get into the market. And the other thing is, yes, biomass-derived polymers would require more support by governments, so that governments actually can actually support the use. For example, as in some parts of the world it is discussed, for example, to have polymer taxes for plastics, which would make, for example, you can do this for fossil fuel-derived plastics to make them more expensive. You can do it for all types of plastic, because all plastics have an environmental impact. And you say newly produced plastics require a tax, while recycled plastics you can leave out of that. And if you do this, you might achieve that, because biomass-derived plastics are anyway more expensive than fossil fuel-derived plastics, that the gap between these two types of plastics becomes smaller, and they get a better chance to be used. Does this answer your question?
Okay, thank you very much. And then there are another question. Another question from Mr. Alija. Yeah. Which one is the most feasible for industrial scale application nowadays, Sensei?
I guess this is about biomass-derived plastics. So, what plastic has the best chance to be produced in an industrial scale? There are already some of the, well, quite some of these plastics are produced in an industrial scale. I introduced the production of polyethylene from sugarcane sugar, which can be produced, which is produced in the range of 200,000 tons a year. This is about industrial. Other polymers, for example, polylactic acid, is also produced in such a range. So also this one is used, and also for various applications. Then I mentioned nylon 11, which is also, I think, just produced by one company, but it's available. Also, polyhydroxyalkanoates are produced. I not sure about the size of the industrial processes, but they are produced and they are also used for packaging applications. When in cases for products which want to show that they are green, then you do not use, for example, polyolefins, but rather you use them a little bit more expensive polyhydroxyalkanoates. If the product is more pricey, it doesn't matter that much in this case. So you make use of this for several applications, and they are available.
Okay. Okay. Thank you very much. This is many questions I got it from the audience. The next one is from Dina Wahyu Indriani. She was one asked about what the process and or something solvent or a polymer agent that are used in processing of ethylene glycol to become PET and or PE teraphthalate from biomass slides.
Can you repeat, please? I did not catch the question.
Yes. What the process is and or something solvent or polymer agent that are used in processing of ethylene glycol to become PET.
What the
plastic ethylene?
Yes, for PET production,
yes,
the monomers. Or,
yeah, from biomass.
Okay, so so as I said that you can produce for polyethylene terephthalate production, you need ethylene glycol and terephthalic acid, and the ethylene glycol is quite straightforward, quite easy to obtain from ethene and also so from bioethanol. It is more difficult to obtain terephthalic acid from biological or from biomasses because terephthalic acid, the classical process of terephthalic acid production is the oxidation of xylol and of xylene, and this can be obtained quite easily from fossil fuel. So you can get actually a sufficient amounts from fossil fuel. This is more difficult when you come to biomasses because you cannot access directly terephthalic acid from biomasses. Therefore, you need quite difficult processes, quite difficult syntheses, and this makes actually the process of terephthalic acid production from biomasses quite not viable, not feasible, unfeasible, and therefore it might be better if we think on biomass that maybe instead of trying to produce terephthalic acid from biomass, it might be better to look for alternative decarboxylic acids, which can be easier obtained from biomass and which could be used to replace terephthalic acid. As I gave one example from the production of lignocellulosic material, where you got the where you got as an example pyrone decarboxylic acid, which could be used for the production of polyester. However, by my knowledge, this was not tried yet, and it is the question how resistant this polymer that could be obtained from this material, how resistant this would be, for example, to hydrolysis, and if this can be used instead of PET.
Okay.
Does this answer your question?
Okay, thank you very much. Now, another question is from Vilayati. This is he is a master student in agriculture engineering. She asks about which renewable plastic that have high commercial economic and low cost production between starch, mix it,
yes,
PLA plastic, yes, and PBS plastic, PHA plastic, or wood plastic, wood waste, yeah, wood waste. Yeah.
Can you repeat the end of the question?
Yeah, this what's that? Which renewable plastic that have high commercial economy and low cost production between starch mix, PLA plastic, PBS plastic, PHA plastic, and wood waste, and what challenging for next generation for renewable plastics?
So you want to know what is
which ones renewable plastics with high commercial economic and low cost? Yes.
Yeah. So which plastic, which bioplastic could be produced at a low cost and could be successful for many applications?
Yes.
Okay. So low cost is at first thermoplastic starch, which is already used. Maybe you know this. Some companies provide packaging where they say you can eat the packaging. This is thermoplastic starch mainly. So it is for low quality applications. Thermoplastic starch is a good way because it is cheap, and when you think only on packaging, it fulfills its task. If you need more advanced properties, it becomes difficult because commonly producing biomass-derived plastics is commonly quite expensive, and the reason for this is that that you need to reduce the price. You need to produce a lot of plastic. You need to have a large process. For a large process, you need sufficient input materials, so the biomass. And this is a little bit the problem, as you have seen in my talk, that you need, for example, for the production of 100,000 tons of polyethylene, you need an area of about 350 square kilometers, which means you have not just to do agriculture on a huge area of on a huge area, but also when you produce this biomass, you have to transport it then to the production facility over a distance of several hundred kilometers. And another disadvantage of biomass is that probably not in Indonesia, but in many other countries, you have seasons, which means you have a harvest at a certain point in the year. And you can only harvest, for example, when on the north part of the globe, you can only harvest in autumn. And that what you harvest in autumn has to be sufficient to make for your production all over the year, which means you are dependent on the weather, on the harvesting conditions, how much can you harvest in a year, and you have also to store all the materials. When you think on a production where you want to produce some 100,000 tons of plastic, you have probably to store some million tons of biomass over the whole year. And this makes processes expensive. And this is this is also what is the task for the future. I mean, we have to replace fossil fuel derived plastics by other materials, and therefore biomass is one option. It's probably the most important option, but we need to think about the logistic side of the production. Does this answer your question?
Okay, thank you very much for your answer. We have more question. Is it okay, Sensei?
Yeah, I'm fine.
Okay, this is from Stella. Yes, from Stella. She asked about if he make HDPA from bioethylene, and will it call bioplastic too? Will it call the bioplastic too? Will the HDPA produced from bioethylene will be easier to degrade? Also, is the production line similar to petro HDPA? This is his question.
Okay.
Yes.
High density polyethylene.
Yes.
Yes. So when you think on the production of polyethylene from biomass, the only thing that changes is the source of the polyethylene. So the polyethylene from the conventional plastic production is from fossil fuel. It's derived from catalytic cracking of naphtha. And when you go to biomass, the source is from the fermentation of biomass, and you obtain ethanol. From ethanol, you get then ethylene. After that, after you have obtained the ethylene, the process remains the same. So you cannot distinguish between polyethylene that is produced from fossil fuel and polyethylene that is produced from a biomass. After the polymerization process, it's completely the same. And therefore, also the biodegradability does not change. It's almost not biodegradable, or it takes a long time, independent from the source.
Okay. There's a question. This is from Marta. If you want to know, in the PHA process, yeah, there is the the process called powdering process. What is the function of that?
Of what?
This process called as powdering process. PHA process is it?
Uh-huh.
PHA process, yeah.
I will have a look.
In PHA process,
Yes.
there is this process called as a
powdering
process. Yes.
Yes.
What is the function of that?
So yeah, maybe I can once more share the screen.
Yes.
So so I did not really explain this process in detail. So what you do is after fermentation, you precipitate the cells. Then they are then the water is removed, the material is dried, and what you have left over is the PHA and the residual cells of the bacteria. And now you have to separate the cell material from the plastic, from the PHA. And this you do by mainly at first milling or powdering the bacteria so that you crush the cell walls, and after that you are able to extract the polymer. So the polymer is soluble in several organic solvents. So you use an organic solvent to extract the PHA. What is left over is mainly the residual cell walls and other cell parts of the bacteria. Then these are then removed by centrifugation, and by ultrafiltration you get then a clear solution of the polymer, which is after that precipitated by adding another solvent. And then the PHA is separated from the liquid phase by centrifugation, dried, and because it's a thermoplastic, you can melt it and you can pelletize it.
Okay.
So does this answer your question?
Okay. Okay, thank you, Sensei. This is another question also from this Dina Wahyu Indriani, second question. How much percentage of starch, sucrose, and cellulose that we need to get proportional polymers such as PLA?
PLA is produced from sugar. So in maybe you know lactobacillus, which is commonly responsible when milk becomes sour, and these bacteria produce lactic acid, and they need for this, and these bacteria need for this process sugar, so they cannot deal with starch or another material. They need sugar. Of course, you can by enzymes. It is possible to obtain sugar from starch, but by my knowledge, mainly sugar is used. I have to a little bit to close this, otherwise my head disappears. Okay, so the main source for PLA production, or the sole source for PLA production, is actually sugar.
Okay, this more one question is left to my chat. This is also from Tina Wahyu Indriani. How to reduce effectively carbon pollution, during incineration of polymer plastic or biopolymer waste.
Okay, so you want to know how to reduce
carbon monoxide,
carbon dioxide,
carbon
dioxide emissions from polymer waste. The best way is recycling. So if plastics are recycled and the carbon is maintained in the cycle, then it does not become a carbon dioxide. And therefore, plastic should be recycled. And also, there are not only there's not only the possibility of mechanical recycling. We have also to consider chemical recycling, where actually the structure of the polymer is mainly destroyed, but chemicals can be obtained from polymers, maybe even very simple chemicals like hydrocarbons, which can be then recovered and reused. For example, I mentioned earlier also the use of gasification, which can be used for biomass. This can also be used, for example, for plastics, and it can also be used for mixed materials, for example, biomass waste and plastic waste. And from this, you can get synthesis gas, which can be used, for example, for the production of new chemicals. This would be a very efficient way of reducing carbon dioxide levels. So not incinerate the plastics, but reuse them in any kind of way.
Okay, thank you very much, Sensei, for your answer. Okay, I have one question. If we use carbon source from the food, this it means we so for example, this is not enough for our food need. So if we think about the carbon source from the grass, for example, grass, or is it which kind of grass? Yeah, I know that some grasses have high biomass, contain. Yeah.
Yes.
This is all of biomass grass, high biomass grasses produced for grass? This can be used for the plastic, just the polymer, for example.
In this is not so much of a problem of the plastic production. This is more a problem of, for example, when you think on lignocellulosic materials that can be used for plastic production, the first step of using this kind of materials is commonly fermentation to ethanol. Mostly before that, when you use lignocellulosic materials, they cannot be directly fermented, but they need at first an enzymatic process so that the cellulose is degraded to simple sugars, and the sugars are then fermented to form ethanol, which can be then used for example, for the production of ethylene. The disadvantage of biomass for example, wood and grass as biomass is that the fermentation process itself can only convert the material that is derived from cellulose, while the lignin is left over. On the other hand, when the process of gasification is used, the lignocellulosic material can be directly converted into synthesis gas, and everything can be used. But from the point of view of environmental impact, both processes, fermentation and gasification, are quite comparable. They have not so much. They have very strong differences in their processing, but in their impact, the environmental impacts are quite comparable. So there's not an advantage of one over the other, as I think.
Okay. Okay.
You wanted to know about what kind of grass would be good, and commonly you can make use of any kind of grass. Well, I mean, there's two things that you can consider. One is you want to grow grass, especially exclusively for the production of biomass. Then you would probably choose a type of grass that provides a lot of biomass over the year. The other thing is you obtain grass as an organic waste material, for example, from gardening, or also from inside the cities. When you have parks or something like that, then you commonly have also residual biomass, and also from there, in this materials you can use, for example, for the production of bioethanol. Does this answer your question?
Yes, thank you very much. Okay, we have time about 14 minutes. If you have any question, please let me know what's your question, or you are directly asked to Associate Professor Guido. Yeah, it's enough. Any question from audience? You can ask directly to Professor Guido. We have 40 minutes left. Oh, you can chat to my chat. I will have to deliver your question. Okay, one question, Professor Guido. This is from Lur Devianto. This is PhD students from Tokyo University. It's from my staff.
Mm-hmm.
This year is new students, PhD students.
Okay.
This he asks about the. Could you explain more about the prospect and challenge for a renewable polymer for lignin and waste?
You want to know how we can make use of lignin for polymer production?
Yes.
Yeah, this is a very good question, because lignin is quite abundant, and it is produced, for example, as a residual material, for example, from the paper industry. And until now, it's quite a big problem because no one really knows what useful things can be used with lignin, because it is quite difficult to degrade because of its structure. I showed one possible pathway in my presentation, and where it was found that by stopping bacteria to metabolize lignin in certain ways, you can get to one main product. Another way, again, gasification can be used, and you can also obtain phenolic products, for example, by pyrolysis. Wood pyrolysis is quite a common process in the meantime, which can also be used to obtain a lot of useful chemicals, not just for plastic production. For example, wood pyrolysis oil is used, for example, as liquid smoke for in the food industry. But when we think on the production on plastic in special, then it's still quite difficult task to find a good possibilities to make use of lignin. It's still very challenging.
Okay, thank you very much for your answer. You're very tired because we have 1 hour for answer this question.
Yeah, this is not a problem. I had already one lecture in the morning, so.
Thank you very much.
So my throat is already gets some sour, but it's fine. I'm happy when I can ask questions.
Thank you very much. Okay, I think it's enough for today. Thank you very much for your presentation, for your nice answer for all of our participants today. And now I'll be back to the Master of Ceremony, MC. Yeah, thank you very much. Yeah, I think it's finished for answer to question. Thank you very much, Sensei.
Thank you very much for listening to me and having me here. And I'm very happy that your students are very interested in the topic. And
yes, it's very good. It's very good topic today. You give our to us our good information. Yeah, okay, it's for our knowledge.
Thank you very much.
Okay, I give back to Fabiola. So yeah, MC, thank you very much. Ya, assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much for Mr. Fajri Anugroho and also Mr. Guido Gross for the information and the knowledge which has been delivered and given to us all. May it be useful for us in the future. And finally, we get to the last session in this event, that is closing. To all participants, do not forget to fill the attendance list. The links are already sent on the chat box, so make sure to fill the form which has been shared by the committee. And now, since we get to the closing, let's close this event by saying Alhamdulillahirrabbilalamin. As today's event master of ceremony, I thank you all for the participation and the attention. May what we had conducted will be useful for us all. I would also like to apologize for any mistakes that I might make during this event. Thank you so much, and I hope to see you all again. Wassalamualaikum warahmatullahi wabarakatuh, and good afternoon.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much.